Hello, it's Keith here, and this is lesson 72 of the platform-specific series of my 650 assembly programming tutorials, and today we're looking at the Commodore 64. What we're doing today is we're looking at interrupts. Basically, we've got the previous example, the Mintile series. We made this graphical example there, and we've also looked at Chibi Sound Pro and ChibiTracks, the music players, and we're now combining the two together. And as I say, today's priority is looking at how the interrupts can be used on the Commodore 64 to cause a VBlank style interrupt, which is a timed interrupt once per frame, to allow our music to update at the correct speed so that it sounds the way it should speed-wise. So that's the example we're going to be looking at today. As I say, we're not going to be looking at the graphical part or the actual music playing from the point of view of generating sound. We'll briefly cover the ChibiTracks requirements, the music player that I've written. Anyway, how do interrupts work on the Commodore 64? Well, like most 6502 systems, the interrupts all are fired to addresses at vectors at the high memory area of the system's memory. Now, that is actually ROM on this system. A vector, I should point out, is just a clever term for a memory address. So basically, there's a 16-bit address at a specific position, and when the interrupt occurs, the processor loads the address at that address and then executes it like a jump. So it's not a jump command, it's just an address that is executed. As I say, the problem is, from our point of view, we can't change the address we would like to because it's actually in ROM. But fortunately, that ROM has a convenient point that we can connect to and put our own interrupt handler on the end of. So the interrupt we're going to end up causing today is known as an IRQ interrupt. So this is a standard interrupt which we will cause. This will actually execute the memory address FFFE and FFFF, that's a 16-bit address of course. That's the vector that the CPU will execute, but that address is ROM, and the ROM interrupt handler will actually pass control over to the address at address 0314 and 0315. The 16-bit address at that address will be the IRQ that is caused by our VBlank. So all we need to do is put the address of our interrupt handler at 0314 and 0315, the 16-bit address, and that will be fine. A slight quirk on the Commodore 64 is that it actually pushes some of the registers for us. It actually pushes the accumulator and the X and the Y register, very kind of it, because we were going to push them anyway. So I've actually downloaded the disassembly of the ROM file from the internet. We're just going to quickly take a look at it. So here is a disassembly of the Commodore 64 ROM, and you can see you've got the various kinds of interrupt here. And it's this one at FFFE we're going to want to look at, this address FF48. This is the interrupt handler code for the actual that the ROM actually executes. So here is the start of the interrupt handler, and you can see we've got a push of the accumulator, then we're transferring the X to the accumulator and pushing that, effectively pushing X, transferring Y to the accumulator and effectively pushing that. Now what we're then doing is we are transferring the stack pointer to X, and we're then effectively loading into the accumulator the flags. Now the flags are automatically pushed by the C64 when an interrupt occurs, so this is effectively loading the flags, and it's then testing what is effectively the break flag within the Commodore 64, within the 6502 flags. Now the break flag's a bit curious. It never actually sets within the processor flags. It is only set in this pushed value onto the stack here. So this is basically testing for the break command. And what's happening here is we're effectively branching if the break flag is not set, and we're branching to here. And this command here will jump to the address at address 0314, not jumping to 0314 itself. So this is what's happening if there's no break. If there's a break, it will be this address here. So all we need to do is put the address of our interrupt handler at memory address 0314, and that will do the job that we want to do. Okay, so that's all we need to do for getting the interrupt and handler installed. We then need to set the interrupt up, and we'll look at that as well. Let's go over to our source code. Let's check it out. So this is the file we're looking at today. So the first thing we need to do is we need to have an interrupt handler. We have one, and it's called, incredibly imaginatively, interrupt handler. You could have never guessed that. And so what we're just doing here is loading the 16-bit address of our interrupt handler to 0314 and 0315. That's all we need to do. The interrupt handler is now installed. Very good. Now what we need to do next is we actually need to set up the interrupt so that the VBlank interrupt will occur. Now the first thing we're doing here is we're actually disabling the alternate interrupts from CIA1 here. So we're setting the bits here to stop the interrupts from CIA1. Now what we're then going to do is we're then going to set up what is known as a line interrupt. So basically we can cause an interrupt to fire at a specific line of the screen. Now this could be used for things like sprite relocation, but in our case we're going to use it very simply just to detect the start of the screen draw. We only want this to fire once per screen. So we're going to set the line that we want the interrupt to occur as line 0 at the top of the screen. Now, of course, it doesn't matter what line it actually occurs, as long as it only occurs once per screen. If you were going to have a sort of split screen effect in the middle of the screen, then the interrupt handler would fire twice, and so you'd only want to update the music every other interrupt, so you would need to cope with that. But in this case we're just going to have a single one at line 0, and then we're doing that with D012. Then to enable the interrupt we need to use D01A, and it's the bottom bit here that I've marked with an R here, which is the raster line interrupt. So this will now cause the interrupt to fire, and that will cause the interrupt handler that we've installed to address 0314 to be executed. Okay, let's take a look at that interrupt handler. Well, here it is. There's not very much to see really. The only thing that's particularly interesting, I would say, is the fact that we have all of these pulls and no matching pushes. Now I've copied this interrupt handler template to all the other systems, and a lot of them would have the pushes, but of course the firmware's pushed half the stuff for us, so we just got the pulls and no pushes. We do have an RTI because remember I said the processors will automatically push the flags onto the stack. When we return, we're going to return straight to our actual executing code, not the firmware, so we need to make sure we actually take those flags back off, and it's the RTI command that does that. Now, my music player is ChibiTracks, so we are using ChibiTracks Play to update the music. This uses some 16-bit entries in the 0 page marked HL, DE, B, C, I, and IX. These are pairs of entries that I use like Z80 registers. So I've got a macro here called push pair and pull pair to pull and push those pairs conveniently. Now, once we've finished updating our music, we just need to clear all of the interrupts, so the interrupt handler doesn't execute again until the next interrupt occurs. And so what we're doing here is we are basically doing that by reading in from DCOD and DDOD. That clears the CIA interrupts. And then what we're doing is we're effectively clearing bit 7 of D019, and we just do that by doing a shift to the right. Now that will clear all of the interrupts, and that means the interrupt won't fire again until our next expected execution. Now if I disable these clear commands, I'll just do that. If I run this again, you can hear we've got an awful noise, and the graphics aren't working, and the reason for that is the interrupts are basically firing over and over again, so that as soon as the interrupt handler returns, the interrupt is still there, and the CPU then executes the interrupt handler again and again and again. No time for the graphics to execute, and so the music is playing too fast as well. So that's how we can use our interrupts. So now all I'm going to do is briefly discuss ChibiTracks and just tell you how to get that working if you wish to do so. That's my music player. So basically there's a couple of things we need. We need the platform specific sound driver, Chibi Sound Pro, that's what it's called. That is the driver for each system, the Commodore 64 in this case. So that's the hardware abstraction that makes the particular hardware play in the same way for each of the systems. Now the ChibiTracks is common to all 6502 systems because the Chibi Sound Pro is doing the platform specific work. So this is the music player, and that uses a tweener and fraction 16, which is just some fractioning code for calculating the in-between notes for its playing. So that's the player. We need a song, well, it's called song 1 in this case, and this is the binary file for the Chibi Akima's theme that's being played today. Now, ChibiTracks does need some memory. It needs about 128 bytes of memory for the platform-specific driver and also the music player. So we're defining a memory area here for Chibi Sound. We are defining some pointers to the various variables that ChibiTracks uses. So they're just being defined as offsets within this memory block just for convenience. We have a few options. We have ChibiTracks allow relocation. This allows a binary file to be loaded into a different destination. Now, music files are created with ChibiTracker Pro, my free music player. It's written in .NET. You can download it. And when you create a file, you can export a binary file. And that binary file, when it's exported, it has various offsets within the file for the destination location of things like the the instrument list and the pattern lists and things like that, and they are all coded as a memory address based on the intended load base address of the song. Now, doing that will make a smaller player using these fixed memory addresses, but it's very inconvenient because on the Amstrad CPC I might want to load my song at memory address at 8000, but on other systems that might be the screen memory, so I can't load it at that address. And so either you need to re-export the binary file over and over again, or you enable allow relocation, and the player will actually work it all out at playtime. It'll create an offset and calculate the offsets. Calculating the offsets is a little bit slower and takes a little bit more memory, but it's more convenient, so I would suggest you keep that enabled. Another option is allow speed change. This allows the song to have its speed changed at playback time, and that's very handy if you've got 50 and 60 hertz combinations, or if you need your game to actually speed up the music as part of the gameplay. So if you need that, you can enable it. SMS transpose is for systems that have trouble making the lower tones. You can shift all the notes up one octave, and on this system I have done that because it makes the music sound better, although it's not the correct pitch as intended, but the pitch of all the notes within the song will all sort of be consistent. Whereas if you disable that on a system where there's the low tones aren't so good, some of them will all sound the same, and so it won't sound as it was intended. So I think on this system it's better to have that enabled. Now, when we want to play our music, first we need to run Chibi Sound Pro init. That initializes the platform-specific driver. So that initializes the hardware, and then we don't actually need to do this anymore. That was for an early version. We'll just run that out. And then we're loading in the address of our song into the song base variable, which is the song that ChibiTracks is going to play. We then run ChibiTracks start song, and that will now initialize the song, read in all the variables, calculate the offsets if required. And then all we need to do after that is use ChibiTracks play to actually play it. Now, one last thing I do want to just quickly show you is how you can actually change the song speed. Now, you can set this song speed variable. It will be set automatically by start song, but it will be loaded in from the binary file, but we can override it, and in this case I'm overriding it with a value of 6. Now on this system it will make this song play a little bit slow. If we just wait there. It doesn't sound too different, but it is slightly slower. Now on a system that's 60 Hz, that would actually make it play the correct speed. But if I change this to a value of 3, the song will actually play quite a bit faster. And this could be handy if you're doing something like in Super Mario, where the music increases in speed as the player runs out of time. You know, it could be a useful effect. If you don't require that functionality, then you can actually disable it, and that will save a little bit of processing power, significantly more than allow relocation, because it's recalculating the speed every time a note plays, whereas allow relocation doesn't do so much calculation. But if you disable this, the player can no longer change the speed of the song. Now this binary file was exported with the intention of that being enabled, and so now the music is playing too fast. And the reason for that is if you want to disable allow speed change with a binary file, what you need to do when you export the binary file is pre-multiply the song speed into the binary, and then you can you will have to disable this because you won't be able to change the speed, but it will play at the correct speed without the allow speed change option. So that is more convenient if you don't need to change your speed at playtime, if all your systems are the same frequency, and you don't need to do any speed changes as part of your gameplay. So something worth considering. Anyway, there we go. That's all we're covering today. As always, please go to my website, download the source code, the build scripts, and as I always say, you're welcome to use any of it if you can in any kind of projects, even if they're commercial. I always say that just because I want to make it clear. I don't really think my tutorials are really geared to that level of professionalism. I really only intend them for people having a bit of fun, but it's always best to let people know they can do, and I always want to make sure people can make the best of the things they learn if they manage to do so for my tutorials. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.